Hey there, Math Minds! Welcome to the classroom where numbers come to life.
Good day, Math Minds! Today we will discuss the snowflake algebra. Here we have set S and it has an element S, N, O, W, F, L, A, K, E, 1, 2, 3, 4, 5, 6, and 7. And we already know that it is closed, associative, has an identity element, and has an inverse element for all. And now we will explore its subgroups and draw a lattice diagram relating to the different subgroups. In order to know if it is a subgroups of S, subset of S must be grouped and must be same binary operation. To know that it is true that S sub 1 is equal to S is a subgroup of S, we need to know if it is true that it is a subgroup of S, it must satisfy the given conditions, which is the subgroup of S must be grouped, same binary operation. We have this table here. S star S is equal to S. So S is the only element, so we can conclude that it is a group, and it, of course, it has the same binary operation, and S is in the set S, so it is true that it is a subset of S. Next, we have S sub 2, and it has an element as E. So we need to know if SE is a subset of S. S and E is in the element of set S, so it is true that SE or S sub 2 is a subset of S. So now, is S sub 2 forms a group? To know that S sub 2 forms a group, we need to satisfy the given condition, which are it must be closed, it must be associative, and has an identity element, and has an inverse element for all. To know if it is closed, we need to determine that if we operate S to S, the element or the result must be in the set. So we have S star S is equal to S, and S is an element of S sub 2. And we have S star E, and the result is E, which is an element of S sub 2. So therefore, it is closed. Now, we need to know if it is associative. And in this part, we will prove using general form. So we have S star E, S star E, star To prove the associativity, we need to use the general form. There's another way of proving associativity, but in this part, we will prove using the general form. So we have A star B, star C, and it must be equal to A star B, star C. So in this part, we have an element S and E. So S star E star S must be equal to S star E star S. So this will be the group. So S star E, we need to look on the table. We have S star E is equal to E, and E star S is equal to E star S is equal to E. Okay, dito naman sa kabila, we have E star S is equal to E. And S star E is equal to S star E is equal to E. Therefore, it is associative. So we need to know now if it has an identity element. To know if it is or it has an identity element, we need to look at this table. As you can see, there is a part of the table na hindi nagbago yung element kahit pa inoperate sa ibang element. So we can conclude that S is the identity element. Therefore, the identity element exists, which is S. And now that we prove that it has an identity element, we can say that it is possible to have the inverse element. So we know that our identity element is S. So S to the identity element, which is S, is equal to S. So the inverse of S is S. And now E to the identity element S. So the inverse of E is equal to E. And now we can conclude that S of 2 is a group. And it has the same binary operation. So therefore, S of 2 is subgroup of S. For the next one, we have, it has an element S, F, E, and 4. So is S of 3 is a subset of S. S is in the set S, and F is an element of set S, and E is also an element of set S. 4 is an element of set S. Therefore, it is a subset of S. Now, we need to prove that it is a group. So, we need to satisfy the condition close, associative, has an identity element, and has an inverse element for all. In order to know if it is close, we need to operate the element to other element. So, let's say F star E is equal to 4. And 4 is an element of S sub 4. And now we will try another element that will operate to another element. So we have 4 star S is 4. And F star 4 is S, which is an element of S sub 3. Therefore, we can conclude that it is closed. Now, we need to prove the associativity. A star B star C is equal to A star B star C. To prove the associativity, we need to use the general formula, which is A star B star C is equal to A star B star C. So in this subgroup, we will operate S star F and star E. It must be equal to S star F star E. So S star F is equal to F, and F star E is equal to 4. So now in this part, F star E is equal to 4, and S star 4 is equal to 4. Therefore, it is associative. Now, we need to know if it has an identity element. As you can see, there is a part on the table, which is this. Since there is a point or part in the table where the row and column meet and the order of the element stays the same, it shows that there is an identity element. And in this case, the identity element is S, because when it combines with any other element, it doesn't change them. So we can conclude that S is our identity element. So we have an identity element, therefore, the inverse element is possible to exist. So S to our identity element is equal to S. So the inverse of S is S. We have F to identity element, and the result is 4. Therefore, the inverse of F is 4. Then E to the identity element S, and the result is E. So the inverse of E is E. Then 4 to identity element S, and the result is F. So 4 has an identity element F. Therefore, we conclude that all the element has an inverse element. Therefore, S of 3 is a group, and it has the same binary operation. Now we have S of 4, and it has an element A, 4, O, E, 6, F, 2, and S. Now, we need to know if S of 4 is a subset of S. A is an element of set S. 4 is an element of set S. O is an element of set S. E, 6, F, 2, and S is an element of set. Therefore, S of 4 is a subset of S. Then, it must be a group. So, is S of 4 is a group. So we need to satisfy the following condition, which are close, associative, has an identity element, and has an inverse element for all. To know if it is close, we need to operate some elements. So A star 6 is equal to 6. So 6 is an element of S of 4. Therefore, it is close. Now we need to prove the associativity, and we will use the general formula. A star B star C is equal to A star B star C. Since we have the elements A4, 0, O, E6, F2, and S, we need to operate some elements. We have, let's say, A star E star S. A star E is equal to E, and E star S is equal to O. Now, we have this. E star S is equal to O, and A star O is equal to O. So O is equal to O. Therefore, it is associative. Now, we need to identify the identity element. As you can see here, there is a part of the table where the row and column meet and the order of the element stays the same. It shows that there is an identity element, and in this case, the identity element is A. Therefore, we can conclude that the identity element exists. And now, since the identity element exists, the inverse element is possible to exist. So A to identity element A, and the result is A. Therefore, in this S of 4, the identity element A, and A has an inverse of A. Then 4 to identity element A, the result is S. So in this part, 4 is the inverse or has an inverse of S. And O to the identity element, and the result is 2. So the inverse of O is equal to 2. And E to the identity element, the result is F. So E is the inverse of F. O E inverse is equal to F. 6 to identity element A, and the result is 6. Therefore, 6 is the inverse of 6. And F to the identity element A is E. So the inverse of F is E. 2 to identity element A is equal to O. So the inverse of 2 is O. Then S to the identity element A, and the result is 4. So the inverse of S is equal to 4. Therefore, all the elements has an inverse element. Therefore, it has an inverse element for all. Therefore, it is a group, and it has the same binary operation. So S of 4 is a subgroup of S because it satisfies the condition subset of S must be group and must have same binary operation. And now, the last one is S of 5. It is the same as the set S, which is our original set. Therefore, we can conclude that S of 5 is subgroup of S, must be group, and same binary operation because S of 5 is our improper subgroup. And S sub 1 is our trivial subgroup, and S sub 2, S sub 3, and S sub 4 is our proper subgroups. Now, this is our lattice diagram. We have S sub 5, S sub 3, S sub 4, S sub 2, and S sub 1, which are the subgroups of S, and it has an element S, N, O, W, F, L, A, K, E, 1, 2, 3, 4, 5, 6. Now, we can conclude that set S has 5 subgroups. We have S sub 1, which is the trivial subgroup, S sub 2, which is one of the proper subgroup, S sub 3, one of the proper subgroup, S sub 4, one of the proper subgroup. So overall, we have 3 proper subgroups. And S sub 5 is our improper subgroup. Okay, that's all for today, Math Minds. See you next time.